So Ajit mentioned, you can factorize, you get P and Q. What exactly is required to be able to crack the keys? Is it the value of P and Q both, or how does it work? Explain as if you're explaining to a layman.
Right. Let me share something to make that easy.
Yes, I love visuals.
Yeah. So just a small example here. This is an example of, actually, if you don't imagine the grayed out part, the example is of factorizing a number. We are using Shor's algorithm here. And it uses this concept of finding the remainders and finding a period for that. And if we can find the period, which means get a value of 1, then we can actually factorize the numbers. So I'm doing a little bit of a jump that, yes, I'm not proving why, but let's go with that if we can find this, where at what power of 2 we get a value of 1, we have got the period and we can factorize the number we are trying to factorize. In this case, the number is 35 that we are trying to factorize. The challenge is each step has to be done one by one. 2 power 1, 2 power 2, 2 power 15, 2 power so on. And that, as this number is small, 35, so the period is small. As the number gets bigger, this computation can go on forever. The beauty of the quantum computer here, what I'm kind of showing as a diagram, kind of a fuzzy diagram here, is that you can give all these inputs in one shot and get all the outputs in one shot. Problem that happens is now we need to extract, and that's where the example that Ajit gave, it collapses and you will not get all the results, you'll get one of the results, and then you're back to square one. So there is some technology we use called quantum Fourier transform, using the spins and the phases to separate these out and get the specific number we are looking for, in this case 1. And once we have that, then we are able to factorize. Now for 3 qubits, as I'm showing here, it is kind of straightforward. It works fine. There's not so much errors. Even if there are errors, we can check them. But as this increases, there are errors. And then we are not able to do it at scale. I cannot have 100 qubits yet. Once I do have that, then I can really scale this up much faster. Ajit, would you like to add something here?
No, this is quite clear. So this is about factorization, finding factors of 35, which is 7 and 5. Right? There are unique factors. Right? So you're finding a number which divides 35 and gives a remainder 1. Okay, so as we find it out, that number, okay, we are able to factorize that. Right? So that's pretty straightforward. You have P into Q. You want to factorize that so that you get P and Q. Once you have that, then yeah, you have practically found the private key, and you can now break the algorithm, or you can do whatever, impersonation, etc. Right. Very, very clearly defined.
All right. So let me get this straight. The more number of qubits you have, the more number of input you can give.
Exactly.
Is that the correlation in terms of doing the computation in parallel for a large set of numbers and getting the results within a cycle? Does that relate to what you were saying, Ajit, or did I get it wrong?
Yes. So let's say if you have RSA key of 2048 bits, then at least P and Q is half of that size. Okay, 1024. Let's assume it's around that size, right? So now you have to guess that number. So you need significant number of qubits to do that, right? If someone claims that we have a quantum engine with 500 qubits, then I mean you are just a step away. You just double that, and you are able to break that, right? You can have 1,000 qubits to break an algorithm in a very, very practical time, right? So that is threatening, of course. How much that threat is practical, we will see. What all safeguards are provided by the current practices, the way we have built our TLS communications, the way we have built bitcoins, etc. That remains a part of discussion. But yes, with more number of qubits, more you can break it in practical time. Satyam?
Yeah, so just carrying on to Ajit's example, trying to factorize a number of 2048 bits is a sub-exponential problem with using classical computers, which means the amount of time is proportional exponentially to the number of bits. So 2048 bits, if I raise something to that power, you can imagine how big a number it is. It is not completely to that power, it's about cube root of that, but still, it's still huge. It's still in hundreds of bits or thousands of bits, depending on what the key size is. What quantum computer algorithm is saying is, I will reduce it to an exponential time. Now, instead of raising to the power of 1024 or 2048, I'm raising 2048 to the power of 3, which is a much, much smaller number. It's 1000 multiplied by 1000 multiplied by 1000 is just billion. Versus if you raise 10 to the power of 1000, you will just counting a number, seeing a number with 1000 zeros.
Yeah.
That's a huge, that is really the change that quantum computers are promising at this point. As Ajit said, how well we will accomplish it, it's yet to be seen.